Should I begin? Yep. So today basically I will talk about some of the projects which are basically going on, people are doing in HRI, leading by Ashok Sen. So I put a sir because I have to tell many times his name. So without telling, I will tell sir. So mainly after really how to get this soft theorem in D equal to 4 from S matrix, at certain point I will tell about its classical limit, and if I get some time I will talk about also can one understand this as word identity or not. So let me begin. So how really the story starts? So basically Weinberg wrote a paper in 1965 that infrared photons and gravitons. So really he was trying to study some scattering amplitude, and basically if there is some one photon or graviton is coming out and its energy is small, so what the property the S matrix should show. But in that time what was the motivation? So from his side the motivation was that since he can do it, so he will do, because in that time even there was no concrete theory of quantum theory of gravity, so people may ask why you are studying those problems. And if something goes wrong, then we will look that okay, if something really goes wrong, then what we have to correct it, but somehow unfortunately nothing goes wrong. So why one should study this, this kind of, this was the motivation in that time. But after that the real motivation starts around 2014 to 15 when Strominger proposed the infrared triangle, which is basically he told that actually three different subjects started completely independently in past. One is soft theorem, one is memory effect, and one is asymptotic symmetry. And he told that really these three things are not really different subject, but they are really connected. And the connection is written in the side of the triangles. Like if you want to go from soft theorem to memory effect, then basically you have to do a Fourier transform in the energy variable. If you have to go to the soft theorem to asymptotic symmetry, then basically if you think like, so let's say that if you want to go to from asymptotic symmetry to soft theorem, then basically you have a symmetry, you study its word identity, and that should give you a soft theorem. And like the memory effect and the asymptotic symmetry, you can think of this is like a vacuum transition, like there is two inequivalent vacuums, but both suppose corresponds to, in case of gravity, like asymptotically flat space time. So basically when one soft graviton is emitting, basically you are making transition from one vacuum to another vacuum. This is like okay, like for the, in case of gravity, the leading soft theorem is called super translation, which is kind of a part of diffeomorphism as a function of sphere. And the subleading, they called it super rotation, which is basically a vector field on the sphere, which is also a function of sphere coordinates.
Both of them are asymptotic diffeomorphisms.
Both of them are asymptotic diffeomorphisms.
And that diffeomorphism is generated because one soft theorem hit the boundary.
That diffeomorphism is a symmetry of the asymptotically flat space time.
Yes.
And then as a like now if you study corresponding to this symmetry, if you construct the Noether's charge, you study what is the word identity, and that tells us that basically you are inserting a soft graviton in the in or out state, and that can be related as a property of S matrix.
Can I also think about it in the other way, that you have a soft graviton,
right?
And because the soft graviton will have its own effect on the boundary, then that mediates this transition, mediates this diffeomorphism.
Okay. Yeah, I agree. Yeah, like if you are studying like a scattering process, you can compute classically, suppose what is the gravitational field, and in the leading order you can see that like its transverse stressless modes in the transverse direction, which is like on the celestial sphere, you can write as a pure gauge term. So you can think of this basically making transition from one vacuum to another vacuum just by emitting one soft graviton.
So I take a graviton, I calculate its, I take a soft graviton, I take the metric fluctuation, look it at the boundary on the sphere,
right?
And then I get a very specific diffeomorphism,
right?
Which will be this diffeomorphism.
Exactly, a specific diffeomorphism.
Sorry, maybe you were going to say more about this, but I didn't quite understand this vacuum transition thing on the third arm.
Okay, this is basically like if suppose one gauge field component at the boundary, if suppose this is like, let me tell, so suppose on the, like if you go to large distance from the scattering center, some scattering is happening, and this you define a celestial sphere, and on the boundary you can define what is, suppose for photon case, let me tell for simplicity, that you will get like Az or Az bar, this Z bar are the coordinate on the sphere. So for this, like for the leading soft theorem, what happens is that for due to this, if you compute this Az field on the boundary, you can write this thing completely in terms of del Z times some function lambda, which is function on the sphere. So now if this Az is really a pure gauge, right, then the field, it will not affect at least the field strength components which are on the special infinity. So basically like you are making like a pure gauge transformation, which is not observable, but really you are going from one vacuum to another vacuum, one Az value to another Az value. So in that sense, this is kind of a vacuum transition. Because you started with a vacuum expression value of Az, which suppose like you started with 0 at the beginning, after radiation you got different Az value.
Are we thinking of this lambda as some kind of singular, not it's pure gauge, but it's singular, like in the case of Dirac monochrome, and the vacuum transition is like some theoretic level monochrome. In what sense is it? Yeah, so if it is completely a pure gauge, then there's no effect of this. But presumably these are, because these are large gauge transformations.
This is a function of x hat, but it does not vanishes at the boundary.
Yeah. So you're saying lambda being there versus lambda not there is like a different vacuum.
Yeah, it's a different vacuum.
Given by these charges, is that right?
Yes.
So is there an analogy between this and sort of like looking at like different instanton sectors in gauge theory, because there also you have sort of a gauge field configuration that goes to pure gauge at infinity, which ensures that you have finite energy density in space time, and in addition to that, you basically say that what it goes into at the boundary, that when you map it into the sphere the gauge group manifold, then you're basically classified by some quantum numbers, and those define for you superselection sectors basically. So I think I'm saying this correctly, but like I'm trying to understand if when you say vacuum transition, you mean from like zero instanton vacuum to one. Is that a sort of analogy that is helpful? Or?
Yeah, maybe, but the thing is that since we are doing only like the perturbative case, like the perturbative asymmetric, so I don't know like whether these are related to two different instanton configuration as a vacuum. But I think it's perturbative level, basically like this is kind of a gauge transformation, which is like non-vanishing at the boundary, but these two, after like there is some effect when the radiation passes through, so there is some effect change of the mu gauge field. Actually only the what I should tell, only the components which are on the transverse direction, this Az and Az bar, and those basically changing by a pure gauge. Physically, yeah, that much I can say. Yeah. So possibly from this learning, probably what we know really about the infrared sector of the physics, probably we need to learn more. So this is the motivation. So let me start by telling what is the statement of the Soft theorem. So consider a generic theory of quantum gravity or quantum field theory, and consider amplitude with arbitrary number of finite energy particles with arbitrary mass and spin, and this amplitude also contains some number of low energy photons or gravitons, which I will call soft photons and soft gravitons. That amplitude we can relate to an amplitude which does not contains such kind of photons or gravitons, and this relation can be done via expansion in power of soft momentum. Soft momentum is the momentum of the soft photons or the soft gravitons. So this expansion may not be like just power series expansion, it can be anything that we have to determine, and what makes it a theorem is basically this coefficient of this expansion is really universal independent of the theory. So like if we hit at some point non-universal term, then after that really we have to stop, because then basically it depends on really the theory. So probably I don't know that really one should tell this as a theorem or not. Okay. So mathematically the expression, so for simplicity let's consider only one soft photon or graviton. Then basically you have to consider an amplitude which is the n plus 1 point amplitude, basically n number of finite energy particles, and suppose one photon or graviton. Epsilon is basically the photon or graviton polarization, k is its momentum, p are the momentums of the finite energy particles. So this amplitude you can relate in terms of amplitude, which is only function of the momentums and the polarization of the finite energy particles, and it is multiplied by the soft factors, which is this S0, which we will call the leading soft factor, which is 1 over energy of the soft moment, 1 over energy of the soft particle, and S1, which is known at the order omega to the power 0. This is actually in tree level what people have derived earlier. So Weinberg has done for the leading soft photon and the soft graviton factor, he has computed. Then Low computed the subleading soft photon part. Then Strominger, they have computed the subleading soft graviton part, and then many people, including Serre, they have computed for a generic theory of quantum gravity up to subleading order for soft graviton and up to subleading order for soft photon. This is like earlier people have done only for particular kind of theory, tree level computation, but now we know that like it's for a generic theory these factors are true and it's independent of the theory. So
earlier it was done theory by theory.
Earlier, like
because they were not using asymptotic symmetries.
No,
it's become universal because we are using only asymptotic symmetries.
No, it's become universal in a sense that you take a generic theory, like you take a generic 1pi effective action. You don't have to assume which kind of theory it has, but you assume some property of the 1pi effective action which satisfied by all the theories, and just using this, you are doing asymmetric computation, not asymptotic analysis, and assuming only this property, you can derive what is the form of the soft theorem. You don't have to assume a particular action of the theory. You just take a generic form of 1pi effective action, and then you derive it.
What are the powers of Weinberg just for once? Right?
Yeah, here it is a tree level computation, so this is all h cross to the power 0 power.
Now, if you take Weinberg into account, then you will have what will be the statement? Let's say you are looking at, let's say you have good corrections, then does this statement change at all?
If you take h cross corrections,
Right.
yeah, at least like what we have seen, like okay, so like this is in higher dimension or in 4th dimension tree level result. In higher dimension all loop level result, and in 4th dimension tree level result, and there is no h cross here.
So in higher dimensions, just for a minute, for this slightly. So in higher dimensions, if you take this is the answer, including loop effect.
Including loop effect.
So this S0 and S1, none of them depend on h bar.
Yes.
None of them depend on h bar, right? They are independent of h bar.
They are independent of h bar.
Okay.
So I will tell in the next slide maybe what is the strategy one follows for deriving this for a generic theory, but I will not talk about more of this thing because I will mainly focus on 4th dimensional result. So what Serre has given basically the covariantization prescription by which one can derive the result. So the strategy of doing this thing is that you consider the generic theory of quantum gravity. So I am just focusing on, for example, the graviton case. So you consider a generic theory of quantum gravity which can be described by one particle irreducible effective action. At least you consider like a UV complete theory, means string theory, and you write a string field theory action which is a 1pi effective action. And then what you do is that you have to compute using this effective action some S matrix. So basically for that what you have to do, you have to compute some propagators, some vertices. So you have to derive what those things are. So what you do is that you start with a 1pi effective action, and basically first there will be some diffeomorphism invariance. In case of gravity you gauge fix it, then the diffeomorphism invariance will lost. Then basically you expand all of your fields about its vacuum, then you will get a theory which does not have any diffeomorphism invariance. Now you covariantize it with respect to soft graviton background, and doing this you can derive what is the vertices corresponding to finite energy particles and the soft graviton. So you got the vertices, you know the 1pi effective action, invert the kinetic term, you will get a propagator. Now you compute diagrams. Sorry. Okay.
When you say covariantize with respect to soft graviton, you're saying that there's some slowly varying profile.
Yes. So there is some slowly varying profile, and you basically replace this eta mu nu to be eta mu nu plus the soft graviton field. Suppose S mu nu is the fluctuation, and you replace del mu to by the covariantized covariant derivatives. So this is the way how you covariantize your 1pi effective action.
Terms linear in S mu nu, or you'll just keep it as?
Okay, S mu nu is finite quantity, so eta lower mu nu, you can write eta lower mu nu plus S mu nu, but when you write eta upper mu nu, then you have to write all the terms. But suppose you are interested only compute single soft graviton theorem, then actually you don't have to go beyond to derive the vertices. But if you want to go multiple, then you have to take care of all the terms.
So SMU is not assumed to be infinitesimal.
Yes. Yeah. Okay. And for deriving this, one of the assumption goes there is basically this 1 pi effective action. I would say this from the 1 pi effective action, if you compute a 1 pi vertex, that vertex should not contains any soft momentum in the denominator. That is what we assumed, because that is what we expect also for a local kind of theory, that the propagators only have the 1 by momentum factor but not the vertices. So, but what I want to show is that due to the infrared divergence property in 4th dimension, this is the statement which precisely breaks down. So, this kind of construction we cannot follow in 4th dimension. So, this is just one diagram which can appear like these dot lines are basically the scalar particles, and this is suppose for example photon or graviton, whatever you want to take. There is suppose one graviton. So, basically this is in kind of a one pi effective vertex with one soft graviton is attached. One part of this is this. Now, if you see, if you do the power counting, suppose you want that the momentum of the loop L is smaller than the momentum of the finite energy particles. In that limit, let us compute this diagram. You will see that including K.
Okay.
So, if you just do the analysis, like since these lines are on-cell lines, so if you just put P square plus M square equal to 0, what you will get is this factor. And this you can see goes like 1 over L to the power 4 kind of thing, and when basically this loop momentum is in order of the momentum of the gravitons, soft graviton, then basically it gives like 1 over mod K. But you started with the assumption which is basically the 1 pi vertex should not contain any 1 over momentum. So, in 4th dimension this precisely breaks down, and if you want to compute like this is for single soft photon or graviton, like if you want to do for double soft photon or graviton, then in 5 dimension also you will get such kind of factors. So, like so basically the thing is that infrared, like due to this massless particle running in the loop in 4th dimension we are hitting this problem. So, we have to cure it, but probably something more to it, even not only the 1 pi vertex but the S matrix, that is also problematic in 4th dimension.
And this same counting will say even the IR parts in higher dimensions will not have this.
Yes.
And UV part, the
Yeah.
UV part of this gives the usual soft theory.
Yeah, the thing is that in UV, since we are considering like a low energy theory, like you have some UV complete theory, we are considering in that limit integrating out the massive fields, you have a 1 pi effective action. So, we are not bothering about what is the UV thing.
Yes.
We are only looking at the IR regime.
Yes, we are looking at low energy theory, but this loop momentum can be at the order of the soft momentum, or it could be higher than the soft momentum.
Yeah, loop momentum can be have to less than the momentum of the finite energy particles. It can be higher than the soft momentum, and it can be also lower than the soft momentum.
So, the part that is lower than the soft momentum gave you the log behavior in 4D.
Lower part of the soft momentum, then you will get here Pa dot K, that will give a log behavior.
Yes, and also you have another part which is the part which is larger than the soft momentum.
Right.
So, larger than the soft momentum, but does it contribute to the soft theory?
Yeah, so yeah, larger part of the loop, if the loop momentum is greater than the soft momentum, that will also contribute.
And they will contribute exactly the same way as higher dimensional soft theorems. So, higher dimensional soft
No.
theorems has their own structure, and this larger momentums will give you the similar structure.
No, the thing, okay, so the thing is that, yeah, I understand your point, like that the thing is that in higher dimension, like suppose for example you are considering the loop momentum is greater than the energy of the external photon, then you will get here like d to the power 4L by L to the power external soft photon. Then what you will get is basically d to the power 4L upon L to the power 4 here, right? So, this still gives a log divergence.
You in higher dimensions?
No, in 4th dimension. In higher dimension it will not give.
Okay. So, in 4D, the part which is larger than the soft momentum, that part will also correspond to log divergence.
Exactly. So, there is two parts. One is when this loop momentum is smaller than the external graviton momentum, and also when it is in between the PA and the external graviton momentum. So, both things we have to take care of.
Both of them gives log terms.
Yeah, both of them will give log term, but we will develop a technique where basically we can remove one of them from both sides of the matrix. I will tell later.
So you get 1 over mod k
Yes.
from this diagram.
Right.
But what's wrong? You are looking for a 1 over omega anyway. I mean, am I missing something?
No, no, yeah, you are right. But this is your 1pi vertex, but right, there will be a propagator and all these things.
Yeah.
And this propagator will give you also 1 over pa dot k. So this suppose like I am telling like this diagram. So this is only the vertex factor, and which I will use to compute only the tree level diagrams. So like then basically in the tree level diagram, this is a 1pi vertex, and you have a diagram. This is 1pi vertex, and there can be any scattering process. So this is basically is an intermediate step. Now suppose one soft graviton is coming out. This is suppose momentum PA, PB, all the things. Then here it will follow like a momentum like PA plus all the P's plus this K. This propagator will have a factor, right, which has also 1 over K.
No, so you're saying there is an internal line which is 1 over k. Is that this equation means what?
This is about the vertex.
This is about one part of the 1pi effective vertex.
Yeah, so where is the problem?
No, the problem is the vertex has a pole at 1 over momentum.
Usually the propagator has a problem.
Propagator has a
Here he has a problem at the vertex.
The vertex gives you a pole, which in normal cases
it should not. Means this earlier derivation assumed this thing that the vertex should not give any pole in the 1pi vertex. But this is like violating in d equal to 4. So we have to reformulate our analysis in 4 dimension especially.
So if you remove that pole, I mean, right now it's what, like a 5, let's say this is a 5-point amplitude,
Right.
right? And if you remove that guy, it
Mhm.
becomes a 4-point amplitude.
Right.
Now, why can't I say that this particular 5-point amplitude
Mhm.
with some soft graviton or soft photon coming out of it
Mm-hmm.
should have the structure of 1 over omega
Right.
times some other stuff.
Right.
So, and you seem to be getting some 1 over omega from it.
No, no, yeah, I agree. So what I am telling is that don't think this as a full amplitude, but this is a vertex which is because once we have 1pi vertex, we will only allowed to compute the tree level diagrams. Tree level diagrams will give us the full result of the loop amplitude. So this
so
is
you're saying you are including loops here, is that?
yeah. This is the include means this is one part of the 1pi when we compute the 1pi vertex on cell.
Yeah.
So this is a part of the 1pi vertex, which contains the loop thing. Okay, so let me maybe make my statement more precise. So you have a 1pi vertex. Suppose, for example, let us consider suppose 2 external lines and 1 graviton. This is 1pi vertex. Now this can contain suppose one diagram which is like, for example, in case of graviton there can be make the statement more. So this kind of a process. And this is a part of this diagram. And suppose this loop which is contributing this 1pi vertex contains a 1 over k factor. But this now this is scattering to some another thing. This is going on. So this is the diagram which you have to compute. And in the earlier analysis, what we assumed that whatever this 1pi vertex is there, those does not contain any 1 over soft momentum to derive the analysis. But now we are seeing that this 1pi vertex, one part, is giving 1 over k factor. So the earlier assumption to derive all the analysis, that is basically breaking down.
So you're saying your analysis does not apply to one particle reducible diagram. This thing that you have drawn here is a one particle reducible diagram in which you can just cut that line. Is that the point? No, but that's not,
No.
what you're saying.
No.
I'm
Yes.
using some something.
Yeah, so I'm telling that this is, you can think of so suppose 4 scalar and 1 graviton. This is a vertex, 1pi vertex we want to compute. So you have first thing what will appear is that all the tree level diagrams which involves 4 of the scalars and 1 graviton is coming out. Next order it will come out this diagram. So you have to sum over all the diagrams to get a 1 pi vertex, right? But now in 1 pi vertex you got a diagram which is giving contributing 1 over k. It can give, but the thing is that in earlier analysis we when we derived the soft theorem we assumed that 1 pi vertex should not give any 1 over momentum. Only the propagators can give 1 over momentum.
That went into the proof.
Yeah, that the earlier assumptions that went into the earlier assumptions to give a generic proof.
But at which order in H bar? Sorry, I keep asking this.
Mm-hmm.
This I agree that you have taken a loop into account
Mm-hmm.
that contributes to effective 1 pi effective action, which
Right.
has a log divergence, which is problematic. But is it not that this has a higher power of H bar?
Okay, probably that one have to count, like, because you know the just I told like the propagators have a like power of h cross and the vertex has a 1 over h cross. One have to really count it, take care of.
Yes, but is it not going to be true that these diagrams you can this will be higher than H bar? Even in this case, can you count it? All I am trying to ask that why you have to take loops into account to get a final answer. Your final sort factors did not have the H bars.
Right.
I just want to understand that even loops can contribute to that.
Okay, so if you count here like number of vertices is 3, 4 vertices. 1, 2, 3, 4. Right? Number of propagators is 1, 2, 3, 4. Right? So all the h cross cancels.
So this will contribute in the effective action. This will contribute to the lowest order in H bar. Effective action can be computed order by order in H bar.
Right.
So this diagram will your claim is this is contributing to the lowest order in H bar
H bar.
expansion of the effective action,
Right.
even though this has a loop.
Yes. Okay. So what we learned is that the soft factorization result is valid for loop level only if d greater than 5 from the earlier analysis, and in d equal to 4 the result is only true in tree level amplitude because loops are giving really problem to the 1 pi effective action. So before going, let me fix my conventions. So I will use this reduced Planck unit that 8 pi g c and h cross I will take 1. Qa I will consider to be the charge of the finite energy particles, Pa are the momentum, and I will always consider that for the outgoing particles these are positive and for the incoming particles these are negative, because of the fact that I don't want to write that sum over the Pa instead equal to sum over the Pa outside, but I will write sum over all the particles of Pa equal to 0 in momentum conservation and sum of all the charges is 0. That is why I am fixing the convention. And I will consider always the soft photon and graviton to be outgoing, and the momentum will denoted by k mu, which is energy is omega, and 1 comma n hat. N hat is the unit vector along which the photon or graviton is emitting. And I will denote epsilon mu by the photon polarization and this curly epsilon mu to denote the graviton polarization. So let me give the results. What we know the in higher dimension, the in higher dimension up to all loop order, this is the results, and in 4th dimension only at tree level. So this is the
Atoms, is it like all atoms?
up to the subleading order, and in the subleading order there is a non-universal piece in soft photon theorem. I have not written that part, only the universal piece I have written.
That part you have.
Yeah, that part I have not written, but we know what is the result.
Complicated part is-
No, this is only tree level. This had in non-universal terms, and how it can come, like there can be coupling of the field strength in arbitrary way to the fields, because field strength is itself gauge invariant, and you know field strength is derivative of the gauge field, so it can produce a momentum in the vertex. So that basically that kind of vertex will contribute to the subleading order of the soft photon theorem. So that is why in case of soft photon in the subleading order there is a non-universal piece, because any arbitrary way you can couple to f mu nu. So that's why in the soft photon theorem in the subleading order there will be non-universal piece, but I have not written it, but one can write it in a general form also. And so this is a n plus 1 point amplitude relating to the n point amplitude for a.
You have written a little bit of that subleading order. The second term is the.
Okay, the spin part, if you want to write, you are right that in the j rho sigma, if one add this spin part, that is also one part of the non-universal piece. Right.
J is just the orbital part.
No, yeah, probably I should tell here J, means I will denote J to be the full part. Then actually one part of this J, the spin part I have included in the subleading order. Okay.
So then at this order, so you're talking about something like sigma mu nu F mu nu.
Right.
The spin magnetic field.
Spin magnetic field.
Coupling, which doesn't come from minimal coupling.
Exactly.
Therefore, it's not universal.
Yeah, therefore it's not universal.
Yeah. So that does or does not come at the second term here.
Yeah, means if you compute the result like subleading soft theorem, that will come in the subleading order. But there can be some other kind of couplings, like since we are considering 1 pi effective action, so you can add also like F mu nu sigma mu nu times phi star phi, such kind of things you can term, and those can also appear in the subleading order. That's why this is just a part of the non-universal piece I have included, which contains also the spin part. This does have one piece of non-universal piece. Okay. And similarly, for the soft graviton theorem, it is actually completely universal up to the subleading order. In subleading order, similarly due to the coupling of the Riemann tensor to the other fields that appears, but at least up to the subleading order it is completely universal, and it is the leading order is basically 1 over momentum, the subleading order is momentum to the power 0, and the leading soft theorem only depends on the particle's momentum, nothing else, but the subleading order depends on its angular momentum also. This angular momentum has a orbital and has a spin part. Okay. So these are only valid, let me tell once again that in d greater than 4, these are valid for all loop orders, but in d equal to 4 only at tree level. Okay. So why people have not done in d equal to 4 the loop level case? Because the S matrix is not well defined in d equal to 4. So why? This is already done in Weinberg's paper, is that like if you consider a scattering process and suppose between two particles one photon is running. So then basically what you do is that let's compute this full amplitude, which is the gamma n, in terms of when the photon is not there, in terms of the, let's call this the tree amplitude. So when the momentum L mu is much less than the momentum of the finite energy particles, you can actually factorize this amplitude in term with this factor times this tree amplitude. And this, let me tell the eta be notation at this moment. So I will consider this eta as our positive if particles are outgoing, and eta is negative if the particles are incoming, just to take care of incoming outgoing both the particles. So in that way you can write if there is single photon is running, and this factor one can compute, and it has a real part and also an imaginary part. Let me don't get into detail because I will do really this kind of computation later, but it has a real and imaginary piece, and now you approximated this integral when the loop momentum is much larger than the finite energy particles. So in the integral you put a upper cutoff which is in the order of the momentum of the finite energy particles, and put a lower cutoff which is like this is IR divergence, so I am putting a IR cutoff which is small lambda. But this is only one photon running in the loop. So if you do any arbitrary number of photon can run in the loop between any legs, so you sum over all the indices A and B, that is what it is done. And then since these photons are indistinguishable, so you have to not only just power by n, but you have to divide by n factorial, and then any number of photons can run, so you sum over all number of photons, then this term will exponentialize, and then it will become this structure that gamma n will be lambda upon capital lambda times this A real plus I A imaginary. Now depending on this real part sign, when you take the IR cutoff to be 0, the amplitude will diverges or vanishes. So really the S matrix is divergent or vanishing when some massless particle is running in the loop. So this is the problem which you have to cure or we have to bypass. So for QED and quantum S matrix, the S matrix is IR divergent, but the thing is that in quantum field theory we know the observable quantity is really inclusive cross section, where you really integrate out, like you put a cutoff, and in the external leg you have to integrate out all the photons or gravitons which has momentum below the cutoff, which is the inclusive cross section, and this infrared divergent piece exactly cancels whatever the infrared divergent piece appears in the loop. So inclusive cross section is finite, your observation is okay. But the problem is soft theorem does not relates to cross section but relates to S matrix. So somehow in the S matrix level you have to do something to make sense of soft theorem. So this is the problem, that is why people have not studied so far this problem. Okay. So really doing the S matrix, let me go few slides. Even before doing the S matrix, from the classical calculation what one can expect in 4th dimension, then we will go to the S matrix and try to do what we can do to reproduce the classical result, and if there is something extra, in classical limit at least this extra should go away. This is the motivation. So let us do first the classical piece. In higher dimension, Alok and Sir, they have done this classical analysis. So let me state what is the classical form of the soft theorem one should expect. So obviously classically when you observe a radiation, it is not a single photon or single graviton. Large number of photons or gravitons to come out to produce radiation. So you have to take really multiple soft theorem and you have to study that large number of photon or radiation should come out. So if you consider this kind of limit, what it turns out is that for emitting large number of photons or gravitons, really the objects which are scattering, they have to be large mass or large charge. And since we are interested in soft radiation, so obviously in the scattering process the energy transfer have to be less, only then whatever it will radiate that will be less, and the energy transfer can less in two cases, like large impact parameter or like probe scatterer limit, when one of the object is big and one of the probe particle is going through.
And exactly what is the relation between charge and energy? You are taking both of them large.
Yes.
At the same order, like keeping their ratio fixed?
No. For soft photon theorem, I need the charge to be large. If you want to get the electromagnetic radiation, if you want to get the gravitational radiation, then you need the mass to be large.
So the respective charges has to be large. Only that is the number.
Yes.
Because that is the only factor that goes in the soft factor.
Soft factor. And yeah. And since
only
like
that is large.
yeah, that is.
Now, if you are taking UV kind of things, then you can charge is very large. Therefore, you need to take mass to be large. Otherwise, it will highlight something.
Right.
Okay.
So yeah. So this is what precisely the classical and soft limit defines. And then like if you want to get like a soft radiation, then obviously the characteristic scale of the scattering process, like if black holes are scattering, then the characteristic length is basically the Schwarzschild radius. Then like you want that the soft radiation's wavelength should be much greater than the radius of the black hole. So if you take this kind of limit, then one actually can show that if you do such kind of a process, completely classical calculation and compute what is the radiation field and do a Fourier transform in time space to go to the energy space, and then you can relate this thing exactly to the soft factor times some normalization. This normalization I have written there, but one can only determine up to a phase factor. The phase factor one have to precisely fix by classical calculation.
And here the statement is that the other non-universal pieces that you didn't write, they
No.
are going to get dropped out in this large charge.
Yeah, the thing is that in large charge or large mass limits, the off diagonal piece in multiple soft theorem, those will like goes out.
But
Means those are
even if
suppressed.
One soft. Let me stick with electromagnetism.
Right.
In electromagnetism, you had a subleading soft photon theory,
Right.
which had non-universal parts.
Right.
And in large charge limit, what happens to that? Is it that all the terms that you haven't written are dropped out, and only the angular momentum part survives? This is why
Yes.
you kept it.
Exactly. Only the orbital angular momentum part.
Only the orbital momentum survives. So this is why you have written it. And in case of gravity, if I take large mass limit, up to subleading, this is universal.
Right.
But then you have subleading, which is non-universal. So at large mass limit, that will also have very simple form.
Yeah, that will be so okay. So maybe I should at least let me sketch what really goes in this the classical limit. So like what happens is that like so in usual soft theorem, if you study suppose n plus m number of, suppose let me focus on soft graviton case. So if there is suppose n number of particles scattering with m number of gravitons, then this you can write as like the leading piece will be S0. S0 is the leading soft factor, m minus 1 times the S1. Sorry, the leading will be whole R S0, and the subleading will be S0 to the power m minus 1 into S1 plus some complicated piece, which is we will call like contact terms. Now what happens is that when you take classical limit, what happens is that classical limits you want large number of radiations should come out. So this in classical limit turns out to be this form S0 plus S1 whole to the power m times, actually I should write gamma n. So you can verify that how this thing will come out. So like what happens, like suppose some scattering is happening and you are observing at a distance, suppose r, along some n-hat direction. Okay. So what you do is that you want large number of radiations should come out. So like you have now, like this is the formula. Now what you do, okay, what is the probability of, suppose I want to observe that within energy range omega to omega plus delta omega, what is the radiation coming out with, suppose delta omega is the solid angle, and within the solid angle what is the radiation is coming out, you want to compute. So what you have to do is basically like the probability will be like, so the soft factor, which is, suppose I am writing this full thing as S. So S to the power 2m, you have to take mod square, and then you have to multiply by the phase space factors in, like that will be omega to the power d minus 2 delta omega upon 2 pi whole to the power d minus 1 into delta omega whole to the power m, right. So this will be, and obviously this gamma n whole square factor is there.
So even in S1,
Mm-hmm.
S1 itself had a long expression.
Right.
And in large charge limit, only a very small part of that remains, which is this angular momentum.
Right. S1, okay, S1 is not a complicated expression. S1 is just in terms of the full angular momentum is there. Right. So let me,
Subleading photon or graviton?
subleading graviton also, like S1 is whatever I have written here, the S1 is. Sorry, this is the S1. This is the S1.
Right, but this is for graviton. For
Right.
graviton, subleading one is a universal one.
Right.
Therefore, it is not very complicated.
Right.
in some sense.
Right.
So
Here
the
I am doing-
formula said if it is photon,
Mm-hmm.
then what would be the statement? Is it the same statement?
It is just the basically whatever the non-universal piece, that will be suppressed. So you only take the universal piece, which is only the in terms of orbital angular momentum.
So in case of photon, you still need to take a little bit of the subleading part, which is the orbital angular momentum.
Right.
But whereas for graviton, you don't have to take subleading.
Yeah, you can take subleading if you want to that up to that much energy. Means there is a 1 over omega expansion.
Leading order in mass, do you need to take subleading in graviton?
Leading order, that depends on up to how much accuracy you want to do. Like it is a 1 over omega expansion. All the terms in terms of the mass of the particles are in same order. But in there is a 1 over m thing, which is 1 over the omega, which is basically telling us the order. So
leading order, let's say.
leading order is like 1 over omega.
Yes.
If you want to take, suppose the like up to 1, then subleading order is omega to the power 0, then 1 by omega. So up to which order of accuracy you want to take in omega expansion, you take that up to that order.
Right. So that defines if it is leading order, subleading order, or subleading order.
Right.
That are the different orders of omega.
Right.
All I am getting confused is that in case of photon,
Mm-hmm.
the universal was the leading one,
Right.
but you still kept one of
But
the
in
little bit
the
of
subleading, there is also universal piece and there is a non-universal piece, and only the universal piece contributes in the classical level. Sorry.
How do you differentiate between what is the universal fit and what
Oh,
is the
because what you can just get from the minimal coupling,
That
that
is
does
the-
not depends on the theory. So that is the universal piece. Okay. So yeah, so what I was telling is that how to take really the classical limit is like you take a m number of multiple gravitons are emitting, the relation of Soft theorem. Then you take classical limit where it can be written as only in terms of S0 plus S1. Then you compute that what is the probability of producing the soft gravitons with soft radiation from omega to delta omega and within the solid angle delta capital omega. So that is what you will get. But now the thing is that since you are really computing like gravitons with a particular kind of energy, so really you cannot distinguish. So really one have to also divide by a m factorial part. And this, let me write it in terms of just a to the power m upon m factorial times gamma mod n square, right? Now you see this is a distribution in m. From maximizing this thing, you can actually get that what is the peak in this distribution, that how many number of gravitons should come out, right? And that basically produces the classical radiation. So if you extremize this thing taking log, what you will get is that m is in order of a. Because if you take log, it will become m log a minus log of m factorial. You use Stirling approximation. What you will get is basically in classical limit, the number of gravitons radiate mostly in order of the a. And a is nothing but soft factor times the phase factor, like the s times this is the phase factor.
So charge is large, m is large.
So exactly. So a is now basically this is completely constant. Now you have the soft expression, like for consider, let's take S0. S0 is like for soft graviton epsilon mu nu E mu P nu upon Pa dot K. There is a sum over A. So you see this, if you like the external momentums are like if you scale by lambda, then this is basically in order of lambda, right? So this is basically telling us that this S0 will large if the lambda is large, right? This is what the assumption which I used. I am giving a justification. And now when you get what is this m is, now you can compute what is the energy is, because energy will be m into omega. This will be the energy with omega, with the radiation omega. But now you can do an independent calculation. You do a scattering process, you compute mu gauge field. From there you know the, in terms of f mu, you know the energy momentum tensor, you compute the energy expression. You compare these two things. What you will get is basically nothing but, like for gravity you will get like the inverse. This is basically trace reverse metric fluctuations and its Fourier transform in time variable. You can relate this thing. This is basically nothing but exactly the soft factor times this normalization. So this is the way how the classical computation is done. So now what happens is that, like, since this is a classical statement and we know we can get the radiation, so obviously the soft factor soft factor is like a finite thing and one can compute. But in terms of asymmetrics, we are really finding problem, right? So since this have to be the truth, and in like 4 dimension we are like getting problems, so we have to cure the problem. So with this motivation, let us try to get, okay, so if this thing is true in higher dimension, and if we assume that in 4th dimension the formula which I have written, these are correct, so then what will happen?
You calculate this classical field using Green's functions.
Yeah.
And then you will take large distance limit, that will give you an expansion in large distance.
I will take only the
motivate you to do what you do at small omega.
Right. So basically I will take only the radiative mode, which is the 1 over r in 4th dimension, large distance, and I know that at least in higher dimension this relation is true, and if we naively assume that in 4th dimension also it will be true, and then this calculation I can do. But what I will do is basically I know that in higher dimension this is the formula of the factorize, this is the soft factor, and I will take its classical limit to compute this thing.
And then from independent Feynman diagram calculations you have to reproduce the same
Result.
factors.
Exactly.
That is one of the challenge.
That is the challenge.
Yes.
Thank you. So the problem, the divergence what we are really getting in the S matrix are incorporated to the fact that, like in S matrix we consider like the states which we are defining at the infinity, they are like free states. But in case of gravity or like QED, since due to the long range interaction that never even at infinity particle does not move at constant velocity. So that is the problem in S matrix which we appear, we know. And from the classical analysis, if we take care of this long range interaction, what we should expect, we want to observe here. So let's assume that the tree level soft theorem, which we derived from generic theory, that contains the full information of the classical soft expansion. So this is what I am giving from now is like speculation and conjecture, but actually I will prove this thing from the S matrix. So if we assume that like in higher time, like the tree level soft theorem gives the full information of the classical soft expansion, then I will take classical limit. That means basically in the angular momentum part, which is in the subleading order, there is a del P mu that I can replace by I into R mu, which is R mu is the trajectory of the ith particle. And if you solve like in 1 by r potential what is the trajectory of the particle, you will get a log t. It is not just x vector is not just v vector of t, but some vector times log of t.
So you are taking at large distances, you have some number of heavy particles.
Right.
At large distances, those heavy particles are moving in some trajectory classically.
Mm-hmm.
So they are, in terms of world line parameter, they have some particular form.
Right.
You are acting with P mu on that particular form. Earlier you are just getting this R mu.
Mm-hmm. R mu I can classically compute in a potential. I have like if someone has given me the Newton's law with certain force, I can compute what is the trajectory.
Right. So for free particles, this will be like velocity. This R mu.
For free particle, this R mu is like the bit like u mu into tau. If tau is your proper time.
Yes, like u is the velocity.
Right.
Now in 4 dimension, if you do the same calculation, you will get some corrections.
Right. Okay. So like, and we know that such kind of even if you solve in 1 by r potential, we know that such kind of log terms is there. So let's assume this is the form of the trajectory asymptotically when sigma is very large, sigma is the proper time, and this CMU is still unknown. We have to compute what the CMU is, but let's take this is the form, and you substitute in the subleading soft factor. You do that, substitute first, basically write the quantum angular momentum in terms of the classical angular momentum, which is like RMU PNU minus PMU RNU, and then you substitute the trajectory. Then what you do is that, so if you do that thing, what you will get like the tree level soft factor, this is the tree level electromagnetic soft factor, and this is for the gravity. So this is the leading order that will not change, but in the subleading order what you will get is a log sigma, not a log omega inverse, and basically the constant velocity part will cancel out because that will be PMU PNU minus PMU, that will cancel out. Only what we will remain is the log sigma factor. Now we are giving a proposal that if you replace this log sigma by log of omega inverse, that will be the soft factor, and if we want to see the radiation of energy omega classically. So the physical motivation behind this is that like if you really want to observe like a frequency of omega, then you should not expect that due to this particle whichever is scattering, basically from the scattering center there will be at radius of omega inverse radius when time is omega inverse. Beyond that, the projected trajectory should not affect your like radiation beyond that trajectory. So like how you can do this? Suppose if you have a like kind of in this place this is log of sigma. If you do a Fourier transform in sigma variable, if you do e to the power I omega sigma, then you can see that like if you take sigma to be large, after like sigma is in the order of omega inverse, there will be like oscillatory function and average out to 0. So only up to the like sigma equal to omega inverse it will contribute. So, but this is still just not a proof. So this is just I am telling that this is kind of a conjecture. If you take like puts log sigma to be log of omega inverse, so that is the form of the soft factors. Still the CMUs are unknown, we have to determine. But the thing is that what we see is that like if you just only substitute, you are getting a log sigma, and if you take sigma going to infinity, it is like diverging. But really from the radiation calculation, you never get any kind of divergence result. So that is why the proposal is if you replace log sigma to be log of omega inverse, and this is what it is telling that earlier like even in like if we assume that this tree level result is correct, or this like in loop level we computed in higher dimension this is correct, basically we assume that there is a power series in omega expansion and we force it. But suppose if there is a log of omega inverse, like at omega equal to 0, you cannot expand log of omega, right? So whatever you forced it, that may not happen, and that like that is like whatever we do wrong, that is what we are getting from the classical calculation. So really without computing the full S matrix, just doing the omega expansion naively will not work in 4th dimension. Okay. So yeah, so I will explain it. So basically now what we have to do, we have to compute the unknown things, what is the CMUs are, and those actually computation of this thing is very simple. Like you consider the asymptotic trajectory of the particles. So to compute the like if you compute the Maxwell's equation like box of mu equal to j mu, you compute what is the mu field, and then you compute field strength. You use Newton's law to derive the particle's trajectory, and then you assume this is the trajectory. You substitute both sides. You can compute what is the CMU is.
And the terms that you didn't write in subleading soft photon theory.
Right.
What happens to those terms? They are not going to contribute this is the most confusing.
Mhm.
What was the motivation? Apart from that they come from minimal coupling, is there an order of magnitude kind of argument that you don't have to consider them? Or is it related to the fact that the field theory you are considering is minimally coupled? Therefore, you need to take only minimally coupled terms.
No, the thing is that when you take the charge, or like for soft photon theorem, when you take the charge to be large, what happens is that this non-minimal coupled term, if you make a from quantum calculation, you have full result. Now, if you do the like large charge limit, you can show that the non-minimal coupled terms which you got, those are like 1 over q suppressed.
Okay.
Means order of 1 over q.
So you forget about it because 1 over 2 suppressed. Now for graviton as well, I can go to subleading order.
Right.
And then I can take 1 by q up to
1 over mass. Mass is large.
1 over mass is ignored, but otherwise I can keep it.
Mm-hmm.
And then I can again try to see that if I am reproducing it or not from classical gravity calculation.
Right.
Just to make analogy, because earlier you had leading order universal, now you have leading and subleading universal.
Right.
But you kept one non-universal part, you kept the leading order term. So here you can do the same and check.
Right. Yeah, from the classical calculation, really, how to make sense of this non-universal piece, that I don't know. Means if you want to do directly from classical computation and try to extract the non-universal piece.
Subleading order, but the one that survives in 1 by leading order in 1 by m. The one that does not have 1 by m.
No, yeah, the universal piece in the subleading order, yeah, that is there, that you have to take care of, that is not suppressed. Only I am telling that in the subleading order in soft graviton, yeah, that is recoverable, yeah. Sorry, yeah, if I make the statement, yeah. So the thing is that in the subleading order soft graviton theorem, there is a universal piece and a non-universal piece. So the universal piece will contribute.
Again, universal piece
The non-universal piece will be suppressed.
And the universal piece in subleading graviton theorem can be recovered from classical analysis.
Yes.
Okay, just
Mhm.
remark about time. So, of course, you know, it's TI-FAR quantum space-time thing, so we are not bothered about the 1 hour limit. But how much more do you have? You have just started more or less.
Yeah, maybe another 1 hour.
Another 1 hour. Okay, so 1 hour we may not quite have, because then we may not have food. So I suggest that you know, we let him proceed more or less, you know, to cover the material, and then. So I myself have to leave, unfortunately, at 12:45 today. But you know, let's try to finish by 1:15. Is that yeah?
Okay. Sure. Okay. So like now the remaining part is to basically compute what is the coefficient of the trajectory, the log sigma, and that you can compute just first you compute the gauge field and then solve the Newton's equation, and you assume this trajectory, substitute in the left hand side, and right hand side you know the gauge field, you know the field strength, then you can compute it and then substitute, and then what you will get is basically the subleading soft factor, which basically takes this form, this with the log omega inverse coefficient. This is the exact form of this coefficient. Okay. So the just one point I want to mention is that in this sum there is only, you see, eta be equal to 1. That means only if the particles are both are incoming and both are outgoing, only this term survives. And this is also like causally what this is what we should expect, because due to the long range interaction, if two particles are incoming, only then they can affect each other. Not a incoming particle cannot affect the outgoing particle in the scattering process, since we are looking at asymptotic trajectories. So let me go to how to compute the CMU in case of gravity.
Wait,
Sorry.
this was, so can you now rewrite everything in terms of the d by dt mu?
No, actually the thing is, okay, yeah, you are right.
Yeah.
One can write this factor just ddp mu into one piece, which have, so let me write down actually what it will look like. So the last sum that can be written as, so there is index is mu and rho, so maybe p up to sign. Sorry, p a mu del del PA rho minus PA nu PA rho del del PA nu times a factor which is like QA QB times PA dot PB upon square root over of PA dot PB whole square minus PA square PB square. This is the form it will take.
You will check it from final diagram.
Yeah, I will check it. So for the case of gravity, you have to do the similar kind of thing. You have to do basically linear, solve the linearized Einstein's equation, and then
One
basically.
thing is not clear. Why this 2-point function calculation, the classical calculation, why does it care about only initial and final trajectory? Why does it not care about what is happening in the middle?
Okay, the thing is that we are only interested in like large time effect. So basically, what you compute is basically when you compute basically like we are interested in long wavelength, and that is basically associated with the large time trajectory part. So if you want to compute like finite wavelength photon or graviton radiation, then really you have to take care of like near the scattering center effects, and that also that actually depends on what is happening near, and many theory dependence things will be there. So soft theorem only can give the information that only from the asymptotic trajectory, if that is radiating, that will radiate some soft photon or soft graviton. So that part can be taken care of in soft theorem. So you can do for gravitational interaction case also you can compute CMU. So let me just tell how to do it. So you have to solve the linear Einstein's equation to compute the metric fluctuation. Then you compute the Christoffel connection. Then solve the geodesy equation of the particle. Basically putting the trajectory which I have told earlier, and then you can compute. But here actually there is a little more subtlety, that though just from the classical part you can get one part of the only log omega coefficient, not the full thing, because of the fact that whatever the soft graviton is emitting, that also feels long range interaction because of the other finite energy particles. In case of QED, since photon does not have any charge, so it cannot feel any long range interaction due to electromagnetic interaction. But Young Mills also there will be, yeah. So, but okay, for Young Mills soft what means I don't know really. In low energy limit what really gluon makes sense or not, because so basically like so that part you have to also taken care of, that whatever the soft graviton is radiating, the long range interaction on the trajectory of the soft gravitons as well. So that part you have to compute, and let me don't go into the details, but what I am telling is that if you compute this thing, what happens is that since the soft graviton is emitting, so what happens is that it will feel a long range interaction by the other finite energy particles, and that is why if you expect that if the distance from the scattering center to the detector is r, so it will never reach at this time r, but it will delay because it will decelerate due to the long range force. So it will reach after some time. So that part actually can be taken care of by a phase factor, because what you will expect like e to the power I omega t will be the phase factor, and it will reach a distance like e to the power I omega r, but with that there will be correction to the phase piece which will tell us that the time delay is happening in the wavefront. But see, this is not containing any omega, and really in classical calculation we cannot get any kind of log omega for this kind of long range interaction of the graviton. But if we do like kind of, this is just from the soft theorem what I am telling, but if you do a independent classical computation, like suppose a probe scatter limit, a black hole is there, and in the background you compute what is the propagator is, Green's function is, and then a probe particle is going, you compute that what is happening to the probe particle, and when it is radiating you also can compute due to this graviton radiation what is it, how it is backscattering within the background which is produced by the other particles. Peters has done the calculation around 1970. So there actually one sees that exactly he recovers this factor, but with this log omega is replaced by log of omega, a log r is replaced by log of omega inverse. So like comparing with his result, we just replace this log r by log of omega inverse. And just I am telling here one point is that this log r you can think of like from the scattering center to the detector distance, and this is basically giving a time delay. With this, for the dimensional analysis, if you just add a log omega inverse term, basically log r omega inverse. So this will basically, since from Peter's calculation we know that basically takes care of the backscattering effect. Like before, since graviton is like gravity radiation is like a wave, so basically in the background geometry it will backscatter before even reaching the detector. So that effect one have to take care of. And then if you add this term with the whatever the classical soft theorem is, the full soft graviton theorem at the subleading order. Sorry.
So I understand this log r coming here.
Right.
And so there is there any classical calculation in which we get the log omega directly?
Yes, basically like this Peters, what I am telling you, like Peters has done a computation in Schwarzschild background geometry. One probe particle is moving, and that is why it will radiate due to the long range interaction. It will decelerate. It will radiate, and then you compute the trajectory of this radiative like gravitational field. Now you should not use the flat space background, but the metric which is produced by the heavy particle, and you use this Green's function to compute. One will get this log omega pi. But since in the classical computation here we are using only the flat space Green's function to compute, we have not recovered. We only get the time delay part.
Log omega and the logarithmic dependence on r just goes away.
No, there will be a log r piece also. With this log r, there will be additional log omega piece. They are with same coefficient.
And you were saying that you are going to ignore the log.
No, that is what is important. But I am telling that we cannot get just kind of naive this kind of computation. We have to do a more rigorous computation to get that.
You are going to replace log r by
Log omega inverse.
You are not saying that log r, of course, has to be log omega r.
No. I am telling.
For dimensional analysis, you need to put something.
No, but that may not be omega inverse. That can be p inverse, the momentum of the high energy particles also. Yeah.
Many other things, but you need to put something.
No, yeah.
I see. So the big, in Coulomb scattering, the big log tail, is a problem. Which is you were saying that log with distance.
Right. So this is, you can think of like in S-matrix analysis, this is precisely the IR cutoff. Because if r distance you have a detector, you cannot really observe a gravitational wave which has wavelength much higher than r. So this is your physical cutoff which you are putting.
Interesting. Okay, unfortunately I have to, please carry on.
Yes, okay. So then this is the full form of the soft theorem up to the subleading order for the case of gravity. This is the leading soft factor, and this is the subleading soft factor which you can get just if you naively assume that up to subleading order the tree-level result is valid, and I told you what is the replacement rules. But this is the extra factor which basically tells us that this log r inverse is basically the time delay, and this log omega inverse is basically the backscattering effect, which we have not able to compute direct classically, but comparing with Peter's result we put this log omega inverse here. And so the physical interpretation of this whatever we get from the classical analysis is basically the fact that since due to the long range interaction even asymptotically particles are not moving at constant velocity, but they are decelerating due to long range gravitational interaction. So due to deceleration it will radiate, and this Bremsstrahlung effect is taken care of by the last line. So let me come back to the S-matrix thing. This is what I want to tell. So the thing is that whatever we got from the classical result, at least from the S-matrix what I will get at classical limit I should reproduce this, but the S-matrix can have some extra thing. In classical limit those should be suppressed corresponding to the classical part whatever we should expect. So the key idea is that we are not really making the S-matrix to be infinite finite. But since we are relating two of the S-matrix, if we can extract the same infinite divergent piece from both the S-matrix, we can cancel from both sides. And we can call that without the infinite divergent piece, whatever the extra piece is there, that is the infinite finite quantity. And then we can give a soft theorem in terms of this infinite finite S-matrix. So the precise statement is mathematically here it is given. So gamma n plus 1, gamma n in 4 dimensions is the S-matrix for n plus 1 point amplitude, like n number of high energy particle and one soft graviton say, and this is the without the soft graviton the amplitude. all of them are divergent. But if you can extract the same kind of e to the power k is the infinite divergent factor. So if you can extract the infinite divergent factor from this, like this S matrix, what you do like in equal approximation, you can extract the e to the power infinite divergent piece factor. So systematically, if you can do from both the S matrix the same factor.
But is it an overall factor or?
Yeah, one in infrared limit one can extract overall factor.
Only an overall dependence.
Yeah, it's only on overall dependence. But always one cannot, so I'm going. But if you can do this thing, then just you write gamma n plus 1 is the soft factor times gamma n, and then you remove both e to the power k from both sides. That's it. But we will see that in presence of gravity, actually this gamma n plus 1 contains not only this e to the power k but some extra piece. So that if that is there, then you have to IR regulate it. And there is a physical interpretation like earlier which I explained, this log r piece, which is exactly related to this IR regulation part.
Compare those structures this with regulator.
With regulator.
So every divergent part is regulated with a distance scale r, and then you compare structure by structure.
Yes. So this is basically the key point which I want to mention, and I will tell details how to really extract this divergent factor. So actually how to extract this divergent factor is actually done by Grammer and ENE in case of QED in 1973, and basically we learned from them that how to really do this thing and how to use this thing in soft theorem, and for gravity we developed that how to do this kind of decomposition and to extract. So let me first focus on the QED thing. So basically what we will do in any of the S matrix diagram, if suppose some photon is running in the loop, we will divide the photon propagator into two pieces. One we will call G photon and another we will call K photon. So okay, how to divide this thing I am telling in the next, I am just telling. So now what happens is that we have to divide in such a way that suppose now each of the, suppose you are computing one loop diagram, that you have to now compute two diagrams, sum of two diagrams, one diagram with K photon and one diagram with G photon. So what will happen? Sorry?
This is for the leading.
No, this is for the S matrix. So I am not telling you how to extract soft theorem. Now for a S matrix, like suppose something is happening here, you have two particles and some photon is running in the loop. This is what was making problem to us. Now I am writing that, okay, you know in Feynman gauge the propagator is, right, this is the photon propagator. You write it two part. One is k mu nu upon, so let me tell the loop momentum L square. So L square plus I epsilon, and one is, let me put I factor also, maybe, plus I epsilon. So what is the claim is that then basically this diagram you have to compute, then basically you have to compute two such kind of diagrams, one with K photon and one with G photon. This will produce this result. So, and why we are doing this thing? The thing is that we will divide this propagator in such a way, K mu and G mu nu, such that if we compute any diagram with the K photon, that will contains the full infrared divergent piece, and the diagram which have the G photon, that should be completely infrared finite. That is the way how we have to construct the K mu nu and G mu nu. Okay?
G mu nu itself will have factors of L.
G mu nu itself have factors of L, and also the where it is attached, the momentum of the particles also. So the thing is that the strategy what we will follow is like what we usually do in case of like to study the OR identity in QED also. Like there basically, if we have like if you have to prove like epsilon mu m mu is equal to 0, like m is the amplitude and you stripped out, sorry, k mu m mu is 0. The amplitude is epsilon, suppose one photon is there, so epsilon mu m mu is the amplitude, you stripped out the epsilon mu and you put a k mu, that is by OR identity that is vanishing. So what you will do the technique, that technique here will go. But here in place of the external photon, you have to cut the propagator, and the propagator which is the eta mu nu, you replace the k mu nu to be, this k mu nu you choose to be L mu into L nu. So the k mu nu is some factor, some b function of PA, PBL, so the momentums are if they are PA and PB. So, and then L mu L nu. okay, and then G mu nu is basically eta mu nu minus this factor.
K mu nu is infrared finite?
No,
Which one was the finite?
all these things are propagator is finite, but when you compute the diagrams with the K mu nu, that is IR divergence. So with the K it is IR divergence.
Factors of L mu nu upstairs. This is the thing.
Yeah, because this B has also a function of L, that you have to choose to suppress this thing. So B, I have not determined what is B. So you have to cleverly choose B so that this contains the full IR divergent piece. So I am just telling that it is proportional to L mu L nu. So this is the first step. So what we will do is that now this is suppose the propagator which is connected to another line, but you just cut it, and then basically you just what you do is that in place of beta mu nu you place L mu L nu. Then suppose this is a scalar line and one L mu is attached. So what this amplitude is like, this is off cell completely. So this is a propagator with 1 plus Pc square plus Mc square. Then there is a vertex which is the vertex factor, and this propagator is Pc minus L whole square Mc square. And you can see this you can write just by subtraction of these two diagrams, where these circles are telling us there is no vertex factor. So this mathematical statement is same as this statement, and this propagator is nothing but this diagram, and this thing is nothing but this diagram. So that means what happens is that if some line is attached, some photon line is internal loop line is attached to scalar particle, you can always sum up of two terms, where one of them is attached in the extreme left and the extreme right. Right? So now suppose there is, this is the simple case, now suppose there is one external photon is also there with momentum k, right? Now basically what you have to do is basically like you have a photon line and it is attached, this is the external photon and this line is attached here. So this diagram you can divide into two parts. One is it's connected here, like let me put the signs correctly, this, and one is like the diagram which is connected here, extreme left and extreme right. And you have another diagram where this photon is connected here, you can write also this and this, and that where the L mu, the K photon is connected here, you write this thing. Then whatever is connecting near here, that actually turns out to be adding to 0. So what happens is that when you sum over all the diagrams, what happens is that only what you will get at the end is basically when the K photon is attached to the extreme right and the extreme left without the vertex factor. So here I have given the expressions for the choice of the B such that what happens is the diagram computed with the G photon vanishes. This is the choice of the B. So obviously with the B you can add any kind of finite term, right? Because you have to only fix the infinite divergent piece, but always you can take some finite piece to add it to call it also divergent piece. So that is what we have used to make the B. So if you just take L mu going to 0 limit, here you will see that only PA dot PV will be there. But we added these L factors in such a way so that we have to compute less number of diagrams. In a sense that if you compute a one loop diagram with a G photon, that basically exactly vanishes. So this is the way we basically have fixed this B factor. Maybe, yeah. Is it understandable?
So you want to capture all the divergences from the K factor.
Right.
But at the same time, you also want to fix the K and the G such that whatever you're computing with the G is also as simple as possible.
Yeah, as simple as possible. Exactly.
The finite part will be just 0.
Yeah.
That's fine.
Okay. But okay, then like what happens is that the statement like what I told is basically like now this is a one loop diagram with suppose a K photon running in the loop. So basically then what happens is that the one loop, this now can be, since it is computed with the K photon, if you compute with the K photon, what happens is that this one loop diagram can be written as only the tree level diagrams times this K electromagnetic, which is just the factor out, the infinite divergence factor completely factored out. And now suppose up to one loop you want to sum over all the diagrams. Then you have to sum over tree diagram and one loop diagram. Now you divide one loop diagram with the one loop diagram with K photon and one loop diagram with G photon. Now you know one loop diagram with K photon can be written as in terms of tree, you add it, you will get this form. This is for one loop. If you go to two loop, higher loop, you have to do all the ladder and cross ladder diagrams you have to add, and finally what you will get, the full amplitude can be written as the e to the power this infinite divergence factor times basically all the diagrams up to that loop order with the G photons. All the photons are G photons. So this is the technique.
For all loop orders.
For all loop order, whatever you want to go to, whatever loop order you can go. Means actually one have to sum over all the loop orders to get the exponential, but this is the full amplitude, full endpoint amplitude. Yeah, and we will call this amplitude computed with the G photons to be the infrared finite amplitude, because this does not contain infrared divergent. So this is what we have done for n point, but we have to do for n plus 1 point amplitude also extract the same kind of infrared divergent factor. Then only we can cancel from both sides.
So when you compute the exclusive cross section, the part that comes from integrating over phase space cancels this.
Exactly this fact. Okay. So like for n plus 1, just what I explained here, basically like suppose this kind of 3 diagrams you have to add, then basically you divide all this diagram by extreme right minus extreme left, and you are left with only these 2 diagrams where this photon is attached to the extreme right and this photon k photon is attached to the extreme left. Now this is off-scale formalism. For asymmetrics you have to do the LSG formalism and you have to multiply by the inverse propagator, and then this diagram will vanish because there is no propagator here, so only this will survive. Then basically if that happens, then basically for the n plus 1 also the same thing is happening, because only like the n point also basically you are moving all this to the extreme right. In the n plus 1 we are moving to the extreme right.
You said that this does not go through for general case series.
Yeah, if there is like photon like graviton coupling, then what happens is that there can be such kind of a diagram where 3 graviton coupling is there. That you cannot do such kind of technique.
Okay. So it just goes through for electromagnetism kind of thing.
Right. Okay. So then since the technique is developed, so let's study the soft theorem using this kind of S matrix prescription. So what we already observed is that the leading soft factor like does not gets corrected by any loop correction, that already Weinberg has given, and we have seen that from the classical analysis that the log omega term is also just a multiplicative factor. So then basically if this gamma n plus 1 will be related to the full gamma n, this is the full divergent S matrix by the S electromagnetic, then we can remove both sides e to the power k, and the infrared finite n plus 1 amplitude can be related to the infrared finite n plus 1 amplitude with the same soft factor. So basically we are studying just for simplicity QED coupled to scalar, and for that case since I have constructed the B such that one loop diagram with the G photon vanishes, so up to one loop only the tree level with the G photon only the tree level result is there. Then you substitute all these things, and what ultimately you will get is that the algorithm to compute this logarithmic term, it turns out to be you have to compute the n plus 1 point amplitude with the G photon, you have to subtract out the n plus 1 point amplitude just tree level factor, that will produce the I lambda times the soft factor. So this is what you have to do by diagrammatics.
Why should we care about this? Say n plus 1 point function has certain divergent structures.
Right.
N point function has some different divergence.
But actually it turns out to be the same divergence
This
factor.
is this example, but in general say they are different. Then you have to multiply by something which might also have divergent factors. So this is like general structure. If you can write it like that, then from classical calculation, this extra factor that you are multiplying, your classical calculation should also give you those divergent structures. Then that is also fine. For gravitons, you are going to do something like that, or
Yeah, I will go to doing something like that, but if there is some extra, then I have to IR regulate it.
yes, IR regulated in a regulated manner. You compare all the structures.
Right.
So it's not necessary that you factorize and cancel. If it is factorize and cancel, it is good.
No, but the thing is that you cannot give a theorem which is in terms of both sides there is some divergent factor. That does not make sense.
At every order in divergence, the structures will.
But you are like relating one divergent factor to another divergent factor, right?
Because in the regulator issue, that it is depends on the regulator which regulator you choose.
No, not only the regulator. Like we are removing both sides the divergent factor, same divergent factor, and we are relating to finite quantity.
But I was thinking once regulator choice is maintained, then you can compare. Anyway,
I guess what he's saying is, if I understand right, the exponential factor which is actually divergent could also be thought of as a regulated finite quantity.
Yeah, you can do that.
Because in general cases, it might not factor out as an exponential.
yeah, I agree. Go ahead.
Okay, so like for example, you have to compute such kind of diagrams, and basically one of the photon is in external, and all the diagrams you have to compute with the g photons, because that is what you have to compute, and you have to take the soft limit to extract. Now what happens is that, like since those diagrams are computed with the g photons, so obviously those are infinite finite. Now to get the log, what you see, if you take the loop momentum which is greater than the energy of the soft momentum but smaller than the finite energy particles, only this regime the integral looks like d to the power 4 L by L to the power 4, and that can produce the log omega thing. And the thing is that when you take L to be less than, then basically this will be some higher finite thing, and that produces omega to the power 0 result, which is subleading corresponding to log omega when you take omega going to 0. So that part we are not interested. We want to extract only the log omega.
Log omega?
So in the integration region, when the loop momentum it is greater than the soft momentum but is less than the hard momentum.
So larger than soft momentum gave you log omega,
Right.
but smaller than
Soft momentum will give you omega to the power 0, because the higher divergent path is already removed. If that is there, then it will be infinite. Okay. So if you compute and sum over all the diagrams, what you will get is basically you can sum over all the diagrams, and you can nicely write that this logarithmic term you can write as this is completely the tree level, the subleading soft factor in terms of the only the orbital angular momentum that is operating on just one integral, and this integral you have to compute. And from there, one observation one can do is basically like, if you naively assume that your tree level result is true, and basically if you this is in terms of the infinite divergent quantity, then you just write this infinite divergent quantity into e to the power k times the infinite finite quantity. Now since in tree level S1 is basically a differential operator, so when it will commute through this e to the power k, it will operate on k factor, and that is what precisely here appears. And what it is telling is that since though this k electromagnetism factor is computed from the one loop, but when you sum over all order it basically exponentializes. So though we computed all this result in one loop, but this is actually valid to all loop order. So this is completely one loop exact. So this is the statement of the full S matrix, no, not only just up to one loop order. So now I am telling like, now if you do this, you have to perform this integral, and one part of the integral actually produces your classical result, but when you take the poles of the photon propagator, there will be extra contribution which you have not gotten from the classical result, and that piece actually takes this structure. So then how you really check that cannot contribute in classical order? So you take classical limit, where basically like momentum transfer is small, or like large impact parameter or probe scattering limit, and you can show that this quantum means, let me don't call it quantum, but this extra piece actually suppressed relative to the classical factor. So we got some extra contribution also. So let me just point out what are the extra thing what you will get in the soft graviton theorem, what you have to take care of the extra piece. And what happens is that in case of soft graviton theorem, in the KG decomposition, if you sum over these diagrams like in QED vanishes, but here it does not vanish. It has some extra contribution, but this extra contribution is infinite finite, not divergent. So you are safe, but it can contribute to log omega, because that one have to analyze. And the other thing is that like due to this 3 graviton coupling kind of diagram, you cannot perform their KG decomposition. So that kind of diagram you have to take care of also the contribution. So now you have to basically compute all these diagrams which are only with the G gravitons, like if you after KG decomposition, but these diagrams you have not performed any kind of KG decomposition, so you have to fully compute, and you have to take care of only the energy range which is basically less than the which is greater than the soft energy but less than the finite energy particles, and in that way you can extract what the soft factor is. So like here the algorithm turns out to be not just this factor but also the 3 graviton diagram containing 3 graviton interaction vertex, and also non-factorized part what is there. So if you compute, it also takes this form, that same subleading order tree level soft theorem operating on an integral, and you have to compute the integral and you can get the result. But here is something more. So this is the result what you will get, and the interpretation is same, like due to long range gravitational interaction particles are decelerating, so it will radiate. So that is the interpretation of the classical piece. But the quantum piece is basically telling us that due to this radiation some energy is the particles are losing some energy, and this is back reacting on the particle's trajectory, and that part is taking care of this quantum result, where basically in classical limit that is vanishing.
Gravitons, sorry, self-interaction of gravitons?
Yeah, that I have not written yet. Yeah, that I have to take care of.
Does that go away in classical limit or not?
No, that part is there because we have seen like there is a from the classical computation, like due to the gravitational, when the graviton is propagating in the background geometry, that is backscattering. So that effect is there.
It will give you that.
Yeah, it will give you that factor. So that basically will come from computing these diagrams. When the here diagram basically when the momentum of the soft graviton is smaller than the energy of the momentum of the loop gravitons is basically less than the energy of the external soft gravitons. In that regime, it will contribute.
Again, you get log.
And again, you will get a log and also a divergent factor. Like you have to put a IR cutoff, and this is the R, and the upper limit is basically the omega. So from the upper limit, you will get a log omega, and from the IR cutoff, you will get a log R. And this is exactly what is there in the classical result. What this log omega piece we have not able to compute, but comparing with the Peters result, we added it. But here you get the full factor, and there is also one extra.
UV cutoff, omega is UV and R is IR.
Omega is not UV. Basically, since these integrals are approximated with energy less than omega, that is why the upper cutoff is omega.
So roughly like UV for this example.
Okay.
I'm sorry, I'm saying
No,
all I'm saying is that whenever you have log divergences come together, like you get UV and IR together always.
Yeah.
Whenever you have log, you have both because it's the same power up and down.
So okay, so doing all this diagrammatics, really what we get new, what we can tell one experimentalist to measure. So this is the memory effect, and what happens is that we know already that from the earlier like classical memory, we know that if some like gravitational radiation passes through, even after long time, if you just observe and all the gravitational fluctuation dies, after that what you will get a permanent shift. So what that means is basically like to start with.
This is the calculation that you have calculated the gravitational fluctuation due to the probe particle.
Yeah.
And then you have waited long enough. Low energy limit waited long enough, and this is the remaining metric fluctuation.
Right.
Which is not decaying to zero even at large times.
Yeah, large time this factor decaying into 0. So the first factor is not decaying into 0.
Some part of it does not decay to 0.
Yeah.
This is called the.
This is what was known in earlier case. This is the memory effect, but the log omega piece basically adds this with the memory effect, this thing which is called the tail term, which is basically telling us that. So I'm just explaining what happening. So when the radiation completely passes, before the radiation happens, you have a 2 mirror in the gravitational detector, and the length is L. After completely passes through, and you like theoretically just you stay there for infinite time. Whatever is that after gravitational passes through, your length between the two detector now changes to L plus delta L.
Delta L because you have metric is changed.
Because exactly.
So you get del L.
Delta L.
Just tell me this metric, how does it depend on time?
This is completely independent of the time. That is what.
Second one is
Second one is like 1 over time.
power law.
Yeah. So basically, like this one is telling that. So this is the effect of the leading soft theorem.
Yes.
This is the effect of the subleading soft theorem. So it is telling that not only that it will shift a permanent shift, but if you wait up to some time, what happens is that it will shift a more, and then with time it will settle down to the permanent shift.
And in higher dimensions, you said, what is the statement of this at higher dimensions?
In higher dimension, the usual sense of memory, like the distance between two detector, that will remain, that will basically have a permanent shift, that will not be there.
So you can see this from the form of.
Yeah, one can see this. Yeah, one can see this from the computation of the metric.
The only thing that went into this classical calculation is the source and retarded 2-point function.
Yes, 2-point function I am not understanding.
Retarded correlation function.
Correlation function, okay.
And you need to take the right causal one, which
Right.
is the retarded.
Right.
So from that form, you can dictate that for any higher dimensional situations, you have no term which survives.
Right. Yeah, that is what one can see. Means what happens, so let me precisely make the statement. So like I earlier told that, so let me tell the expression, like suppose H mu nu, So let me write only the transverse piece. So maybe I should multiply by the polarization tensor. So epsilon mu nu, this omega and x vector, this has the form that omega upon 2 pi I mod x vector times d minus 2 upon 2, if I am correct, yeah, 1 over 2 omega times the soft factor. This was the expression. Now, yeah, no, now what happens in the d equal to 4, omega cancels, but this soft factor, suppose leading order, there is 1 over omega.
Yes.
Right? And now when you have to do a Fourier transform in time space, if you do a Fourier transform omega 1 over omega, that will give a theta of t or theta of u basically, because there is e to the power I, with this there is e to the power I omega dot x vector is there.
But for all higher dimensions, you get a power like
You will get a delta u or delta prime u,
right.
and those at large u vanishing. If there is a theta u,
I agree. So
right,
you get in let's say 6 dimensions. What
you will in 6 dimensions say d equal to 6. Okay, so 8 dimension, what you will get is like, I am counting the omega power. So omega to the power d, like, so this is 8 minus 2, 6. 6 upon 2 is 3. And then 1 upon 2 omega.
One more.
And 1 more due to the S0 factor. So what we will get is linear in omega. And linear in omega, if we do Fourier transform, that will become delta prime of u, t minus mod x. And you see, that means delta prime or delta function, those are really localized about u equal to 0. So at large u, you cannot get a permanent shift. So, okay. So this computation is done like for a process, like if you have a large mass capital M and it is scattering to approximately same mass object m0 and some small mass particles scattering. So for this process, this transverse stressless part of the metric fluctuation is computed from the using the Soft theorem. And now you see one observation just I want to make is that basically this is really the only that along the transverse direction it depends on the velocity components of the scattering particles, right. So if some scattering is happening completely spherically symmetric way, really along a particular direction it will vanish if you take some. So only if there is some asymmetric explosion happens, you can observe this kind of memory effect. Now what happens is that really there happens such kind of asymmetric explosion, like in astrophysics, if you see like type 2 supernova explosion, there basically some neutron star produced with a large kick velocity. That means by linear momentum conservation there may be some other particles which were going back, right, which is basically which we call the ejecta particles, and that kind of process can produce the memory. And that is like in 1987 there in Milky Way there was such kind of explosion, and if we take the data, what it produces is that the permanent shift and the tail effect turns out to be in order of 10 to the power minus 24, where delta is the delta L is the change between the permanent shift and L is the length between the mirror, which is like in case of LIGO, just if we substitute all this data, what turns out to 10 to the power minus 24. But like the current observation of the LIGO has like the resolution in order of 10 to the power minus 22. So like in current experiment one cannot really observe, but we hope that like in LISA, which will be placed in like in sky, probably they have better resolution to observe such kind of gravitational memory. And yeah, so let me finish.